Hello everyone, we are the BURocket team from Boğaziçi University, and today we present to you our mission for 7th Latin American Space Challenge, which is design and testing of an autonomous fluid flow and control system with emergency detection and cutoff. In this presentation, we will share with you our objectives, our mission operational concept, and some technical details. Our project aims to develop and test an autonomous fluid flow control and emergency shutdown system suitable for integration into CubeSat-like form factors. The payload will simulate a fluid transfer scenario under space-like conditions to support the development of safer subsystems. As CubeSats become more popular both commercially and in research, the need for safer payload systems, which will allow a wider range of experiments to be performed in orbit, grow larger. Biological, thermal, and propulsion systems are just a couple of the examples of such experiments. These experiments require precise control of fluid flow and also emergency shutdown systems for the safety of overall mission and satellite in case of potential fails in the elements of the experiment performed. Despite rigorous testing of such delicate experiment components, there might be still faults after or during the launch due to unexpected launch conditions or some faults which pass through the cracks of the testing procedures. This makes the autonomous safety systems more critical as CubeSat field advances day by day. Now let's have a look at our mission objectives. Our mission has four main objectives. Firstly, we will develop a fluid flow system for CubeSat platforms with safeguards against common faults. Also, we will verify autonomous leak detection and shutdown capabilities of the system via data from onboard sensors automatically. Also, we will validate our sensor integration and algorithms for leak, pressure, temperature, and humidity data processing, which are the main data that we will process for detecting leaks, as we mentioned before. Lastly, we will hopefully pave the way for safer liquid-based experiments on CubeSat form factors in future space missions and research.
For the structure, we chose a two-unit configuration, as can be seen from the image. The body of our CubeSat is made from aluminum 6061 T6, and it has a mass of roughly 2,000 grams. The satellite has a modular assembly, which allows us for easier integration and testing processes.
Now let's look at the system architecture. At the center, there is the onboard computer, which is acting as the brain of our satellite. At the top, you can see our navigation and the environmental sensors, including GPS, IMU, and the pressure sensors. At the bottom of the diagram, we have the payload with humidity sensor, leak detection sensors, and the solenoid cutoff valves that execute this autonomous shutdown mission. All the essential data is securely logged on the SD card. And telemetry is also transmitted to our ground station via radio link simultaneously. And the heart of the entire system, electrical power system. We optimize the energy produced from the solar panels with using an MPPT controller and the battery management system. And then we store this energy securely in our lithium-ion battery. This procedure guarantees that every single component, from our emergency valves to the radio modules, receives a stable and uninterrupted power throughout the mission.
Our payload will transfer water from a tank A to tank B via a peristaltic pump. If any anomaly is detected, such as a leak or spike in pressure, the microcontroller will shut the system down and stop the pumps to protect the system against further damage.
For the communication system, we utilize a subgigabit radio operating in the ISM band, paired with a custom-designed antenna and front end so that they can be optimized for our mission. Regarding data transmitted over the communication system, we are planning to broadcast timestamp location coordinates, sensor data, and system status. Additionally, during the recovery phase, the data rate is lowered, which in turn reduces power consumption and increases battery life.
The onboard data handling system, based on a STM32F4 microcontroller, gathers critical data from our temperature, pressure, and fluid detection sensors, detects anomalies, executes emergency shutdowns, and logs information to an SD card, and handles telemetry via a LoRa transceiver to our ground station. Thank you for listening. I hope you liked our pitch video.